talking about the cross product today. And so here we've got this cross product, and it will be talking about, oh, sorry, got a little bit of a, there we go. All right. So we're talking about the cross product and the fact that it is a new operation, very much like the dot product, but also very different at the same time. Okay. So it's written a bit differently. So for example, if I've got A vector and I cross it with B vector, okay, then we will well, have it, you use a different symbol. Instead of the dot, you use an X, okay? And to figure it out, you would do A, okay, magnitude, B, magnitude, and instead of the cosine, you would use the sine of the angle between them, okay? And that is, oops, the result of that. So the sine of the angle between them. And then not only that, there is a major difference, and you would actually, the result of the cross product is a vector. So unlike the dot product, remember the dot product, you took two vectors, you took a dot product, and then the final result was a scalar, just a number, non-vector. Now, with the cross product, the final result is an actual vector. Okay, and the way that it's written is called n, a normal vector, and it is normal to the plane that the other two vectors exist in. All right, so I'll go ahead and draw a picture of it. So let's say I've got a vector A here, and I got a vector B here. The resulting cross product, right, is a vector that maybe comes out like this. And it would be at a right angle to both of those. All right. So if you can kind of imagine what I've attempted to give it a little bit of a three-dimensional feel there. Okay. This vector, this is A cross B. All right. And there are a few things to decide here. First of all, sometimes A cross B could have been like maybe down here, right? Like this, in which case it would have been a downward vector, or it could have been an upward vector, like the one that I've got written there. All right. All right. So that's kind of the idea there. There was a few things we had to decide. What was the size of A cross B, right? So how big is it? It only has two options for its direction. It's always going to be perpendicular to both A and B. And so it points either up or down, like I was saying, okay? Or left or right, but it really kind of, or back or forward or right. It depends on where A and B start, okay? The size of the A cross B, or the magnitude of this vector, depends on the angle, the original angle, right, between these two guys. Whoops, the angle between these two guys, theta. It also depends on the magnitude of A and B, right? And so it really just depends on this, all right? So in the end, the direction of the cross product is normal. It's called normal to A and B. And the magnitude of it is determined by taking A magnitude, B magnitude, sine of theta. And you can kind of take a look at this. What's the sine of 90, right? Versus the sine of 0. The sine of 90 degrees is 1, right? Whereas the sine of 0 is 0. And so you can kind of see that if A and B, if the angle between A and B is 0, then you actually get no cross product. Meaning if A is parallel to B, the value of the cross product is 0. And if A is perpendicular to B, then the value of the cross product is its largest. It's as big as it can get. Okay, so that's a little bit of the idea on the cross product there. Okay, now in terms of some of its properties, well, I just hinted at this. So A is parallel to B if A cross B is 0. Okay? So that's one way of determining if two things are parallel. Remember, there's easier ways to determine if things are parallel. We talked about those in previous videos. The commutative property. The commutative property, remember, going back from above, is that if A cross B is the same as B cross A, and as it turns out, boom, it is not the case, okay? A cross B is not equal to B cross A, okay? And the reason that is the case is because it turns out that A cross B is equal to a negative B cross A. So you can kind of say, so what I'm saying with this one is, remember how we had to decide over here whether or not it goes up or down, right? And we'll talk about what this is here. And so basically, if in this picture that I've drawn here, it looks like I've gone up, okay, with my resulting A cross B, right? And how that works is, the way that our textbook explains it is that the first vector is basically, so you have to use your right hand here, right? And so the first vector would be the well, let me do it like this. So in this picture, what I actually have is, let's see, let me figure out what I've got. I've got B cross A. This is actually B cross A up here. B cross A. Whereas if I get this as the answer, the one that points down, this one would be A cross B. All right. Now, what's the difference between these two scenarios? Well, one's pointing up and one's pointing down. And as you can see, A cross B and B cross A, one is the negative version of the other. You can see that these two vectors are in opposite directions. And so, excuse me. And so, let's explain how I knew that green vector was B cross A and not A cross B. Basically, what you do is you use your right hand. So you get out your right hand, the hand that you write with, unless, of course, you're left-handed. You point your fingers on your right hand, and you put them all together, or I guess your index finger, right? And you point it in the direction of the first vector in the cross product. So if you can imagine me pointing my finger in the direction of the B vector, okay? So I'm actually, now that I'm looking, I would be kind of pointing at my own shoulder on my right hand, if you're following along here. If you're on a computer screen, you would be kind of pointed downish, you know what I mean? And so then the second vector, right here, that's your wrist. So it actually comes out your wrist and points towards your elbow of your right hand. Okay. So you can kind of imagine me pointing my, or you can do it yourself as well. Your index finger is pointed towards the direction of B vector, and your wrist comes out of A, where your fist, your hand itself, is at the intersection of the two vectors. Okay, A and B. Now, how do I know the green? Now the green vector, the result of the cross product, is now pointed in the direction of my thumb. Okay, and so my thumb is pointed up. All right, and so that's kind of what you'd be looking at there. All right. Whereas if I were to switch this, so A cross B is your thumb, right? So basically, the result or the normal vector would be your thumb. All right. Uh, so we could write this down here. This would be the index finger. This would be the wrist. This would be the thumb. All right. There's actually multiple ways of figuring this out as well, right? And so there's, I've got a physics textbook that uses, just different, your thumb, your fingers, and it points out the palm of your hand. So it doesn't use the wrist and various things like that. Okay. So what you'll do is you'll want to be able to explain the direction of a cross product and understand how to determine the direction of a cross product. All right. And it depends on what vector is placed first and then versus second in your cross product. All right. By the way, this bottom vector here, the one that is pointed down, you can see that that's A cross B, because now the first vector would be my index finger. So I'd be pointing sort of up and out this direction with my index finger. My wrist would be coming out down in this direction here. And now if on my right hand, you would kind of see that my thumb would be pointed in the downward direction. Okay, in the downward direction. All right. So there you have it. So basically what that means is the cross product is not commutative, because if you switch the order in which you perform the cross product, you get a different answer. All right. And that's basically that guy there. All right. The associative property. The associative property is this guy. Remember, it's K. And let's do A's and B's here. So A cross B. Right. If I take A cross B and then multiply it by K, it would be the same as taking K A cross B, or it would be the same as taking A cross KB. All right. So basically what that means is you can multiply a scalar with a cross product in essentially any order. All right. And you still end up with the same result. All right. The distributive property. So does the cross product distribute over addition here? So for example, if I've got A cross B plus C, is that the same as A cross B plus A cross C? As it turns out, it is. All right. And so there you have that. All right. Now, be careful. If you distribute in the other direction, you actually have to distribute notice this A vector is in the first position. if you distribute in the other direction, you actually have to distribute, or if you come in from, so if I've got, for example, B plus C here, cross A, it actually is going to be B cross A plus C cross A, okay? And notice the difference here is that the A vector is in the second position under both cases. So you don't forget, if you're distributing in from the other direction, your crossed vector needs to stay on that side there. All right. Let's now take a moment and imagine what the cross product looks like, right? Geometrically. So remember, A cross B is equal to A magnitude B magnitude sine of the angle between them times the normal vector. And that is times, because it's not dot. The reason why it's times is because this stuff out here is a scalar. This is a vector. And this, so as a result, you end up with a vector, right? But remember, n is mutually perpendicular to A and B. So remember, n is perpendicular to A, and n is perpendicular to B, okay? And that's the case. Now, be careful with this statement right here. N is perpendicular to A and N is perpendicular to B. I've seen a lot of students then take this statement and make this assumption that B is perpendicular to A. Be careful, that's not the case. If N's perpendicular to A and N's perpendicular to B, that does not guarantee A and B are perpendicular, okay? Parallelness, it would, but perpendicularity, it would not. Okay, so I'm going to erase this green statement. That is not true. Don't make that assumption. It could be true, but it doesn't necessarily mean that it's true. All right, so what I want to do is I want to basically I'm going to take a vector A and I'm going to take a vector B, right? And essentially, how do we determine this scalar portion of the dot product? Well, let's take a look at what B sine theta is, and just for the purposes of this drawing, I'm going to put B up there and A there. What's B sine theta? Remember, theta is the angle between the two vectors. B sine theta, I guess I should be saying B magnitude sine theta, is that section right there. Okay? And basically, so that's this guy right here. And then A magnitude is this guy, right? So basically what I'm doing is I'm basically making a rectangle with B sine theta on one side and A magnitude on the other side, all right? So here's B sine theta, here's A magnitude, and if I make a rectangle with those two, right there, this is A magnitude, this is B magnitude sine theta, and this area in here is the scalar portion, or it's the magnitude of A cross B. All right? It's just the scalar portion of it, though. Then again, how do you determine the direction, right? How do you determine the direction of the final vector? Well, you would take your finger and, well, it depends. If I'm trying to find out, this is also, by the way, equal to B cross A magnitude. So now the question is, am I trying to do A cross B or B cross A? If I were trying to do A cross B, then I would point my finger in the direction of A, my wrist in the direction of B, and I would get some kind of vector that sort of points up like this. That happens to be perpendicular to both A and B. That would be A cross B. because this is my index finger, my wrist. So you kind of do that, and you would get your thumb would be here. All right. Conversely, if this were my index finger and this were my wrist, then I would end up with this vector, which would be B cross A. They would be the same magnitude, though. All right. So that's what you're looking at there. Let me put my green on top of this, though, just so it looks a little bit more. There we go. All right. So this would be B cross A. Let me put this in B cross A. They would be the same, again, magnitude. Their magnitude would be equal to the area of this box, and the direction would be determined based on whether or not you did A cross B, B cross A, and then how your wrist ends up sort of falling in that whole sort of thing there. Okay. Anyway, let's go ahead and do an application of the cross product. It's torque, and it's the rate of change of the angular momentum of an object. The angular momentum is the rotational inertia times the angular speed. Okay. Well, rotational inertia is, well, it's basically kind of like angular momentum is kind of like the idea of regular momentum. Linear momentum is velocity times mass times velocity, right? This is linear momentum. All right. And the angular momentum, oh shoot, what is angular momentum? I think it's sometimes called, it's a W, right? Anyway, it's the it is the rotational inertia times the angular velocity. The angular velocity could be, your radians per second, how many radians and then the angular momentum is, I believe, a capital I. If memory serves, rotational inertia. Okay. Sorry, the rotational inertia. And that's a characteristic of the shape of the object and different things like that. Okay. And it has to do with the shape of the object, its mass, and how far from the center is the rotating stuff, how's the object rotating, and different things like that. So this would be angular momentum. All right. Now, angular momentum, but just like linear momentum is kind of like how much oomph an object has once it's moving forward, right? Or in its linear straight line. Angular momentum is how much oomph an object has as it's rotating, right? And so kind of imagine sort of some rotating thing and then you walking, into it. You're going to get pretty hurt if it's, rotating fast or if it's a rotating heavy object versus the same idea. So it's the same concept, but it has to do with rotation instead. All right. Well, that still doesn't talk about what torque is. Torque is now the rate of change of the angular momentum. And so if you basically take this as, d dt here, you're basically taking the derivative of the angular momentum, which is the angular velocity times the rotational inertia per second. Okay, this is the rate of change. Anyway, that being said, we're not going to be taking too many derivatives of it in this course because this textbook and our curriculum asks us to not mix derivatives and vectors. Though when you get to university, there's something called vector calculus where you are going to be doing things like taking the derivative of a vector, okay? Which we won't be doing. But whatever, that's okay. We are going to be learning a little bit about torque, though, which has its variable is kind of like a little t, right? And that looks like a J, but it's actually supposed to be a T. Um, and it's got like a little T. Tau, I think, is the variable there. All right. Anyway, you can figure out the torque by doing a quick thing called the cross product of the radius and the force. Radius and the force. Okay. And so basically, we've got some kind of scenario where maybe I've got like a classic example would be if I were to have a bolt, right? Oh, this is horrible. Let me go with a hexagon. I'm trying to draw a hex bolt, right? There it is. And then I'm trying to have a wrench, chiave inglese, if you're Italian here, a wrench around this thing. There we go. And basically, if I try and rotate this, I'm going to give it a torque, right? And let's say I apply a force right there. All right. And this is going to be the radius. All right. And essentially, what we're going to be trying to do here is determine what is the rate of change of the angular momentum of this nut or bolt or whatever it's called. Okay. Why do we want to know the rate of change of the angular momentum? Because we want to know how quickly or is this thing spinning, right? Are we able to change the angular momentum of this bolt? Change the angular momentum of something means also to start it spinning, okay? So we want to start this thing spinning, right? Sometimes you want to take these, nuts or bolts off of whatever they happen to be on, okay? Well, to figure out the torque on this nut or bolt is you take the magnitude of the force times the magnitude of the radius, and you multiply it by the sine of the angle between them. Okay, so here my angle could be this one, right? Or this one here. I could use either one because the sine of both of those angles is equal. All right. And so my torque is going to be, whatever this R is, times the force, okay, times the sine of the angle between them, right? Because remember, our formula is like that, okay? Now, our original formula for the cross product is this guy right here, right? That only leaves one thing, right? Where do we figure out the normal, right? So what direction is the torque on this thing? Okay. Well, remember, the first vector would be your fingers, okay? And, oh, by the way, my arrow for my radius is pointed in the wrong direction. That was a big mistake there. My radius is coming out. That's a key thing. The radius for this thing would be coming out, not in. So my fingers would point in the direction of the radius, right? My wrist would point in the direction of the force, okay? And notice the force is in this direction, so my wrist would be that direction. My fingers would be in that direction. And this is on my right hand. And so you now, what direction is my thumb pointed? It would be pointed down, right? Or the into the the page here. Okay. This is, by the way, this is supposed to be a vector. So into the page. Okay. Because my wrist is pointed. Remember, the first vector is the radius. So my fingers on my right hand will be pointed basically towards the right of this paper. Now I'm pushing down with a force, so that means my wrist kind of comes towards me here, sitting in front of the computer screen, right? And by the way, my computer screen is sort of sitting flat on the desk. Imagine this as if I'm writing on a piece of paper. So that's as I make references to these things. Imagine this screen is flat on the desk. So my fingers are pointed off to the right. The wrist is sort of pointed towards my chest. And therefore, my thumb would be pointed down into the computer screen, right? And that would be the direction of the torque on this bolt, right? And to figure out the magnitude, well, I'd have to know, how much force am I applying? How far away from the center of rotation have I applied the force? And is what's the angle here? So you remember how before we said in order to make a cross product the largest, the angle needs to be 90 degrees. And so now if you've ever turned a nut or a bolt with a wrench, you know that the best way to loosen a nut or a bolt would be to hit this wrench right at 90 degrees with like this green vector here. If I push on it right at 90 degrees, it's going to be the best way of turning it. Another way would be to maximize the length, right? If I were to add maybe sort of like something onto here, like some sort of tube that, adds onto this, and I apply my force here, therefore increasing my radius, you can increase the torque or the angular momentum, rate of change of the angular momentum, or the rate of change of the spinniness of this thing. So if you can actually spin this better. Another way to increase your chances of loosening this bolt would be to have a larger force, okay? So you need a large force, a large radius, and an angle of 90 degrees in order to loosen a bolt the best, okay? And that's kind of the idea. Anyway, or tighten a bolt even as well. Tighten or loosen, either way. Depends on whether or not you're going, lefty loosey or righty tighty, if you know what that is. All right. So anyway, that's kind of the idea of the cross product. All right. So maybe I will now. Oh, I wanted to mention this. This is in geometric. Notice this is my vectors are given to me in this question in geometric format, right? I've got the magnitude of the radius, the magnitude of the force, and I've got the angles at which they are, positioned. So remember, if you're given magnitudes and angles, you're dealing in the geometric formula for the cross product, which is A magnitude, B magnitude, sine of the angle between them, and N, which is basically, thumb, wrist, fingers. Okay. Fingers. All right. That's if it's in geometric. I have yet to discuss what anything that say, well, what happens if my vectors come in Cartesian, right? Remember, vectors could come in Cartesian format, right? So something like 1, 3, 2, and maybe 4, 2, 1. How do I take the cross product of something like this? This would be Cartesian. And you know what? I'm going to put that in a different video, which is basically here, right? Because I'm going to need to do a cross product with some Cartesian stuff down in this example. But this video is long enough. I'll put it in a part 2 for the cross product.